Alright guys, welcome to the video that's going to be all of the examples from lecture 1, which is the common ion effect. Just a reminder of the common ion effect, and the common ion effect says that whenever you have a weak electrolyte and a strong electrolyte that has an ion in common, when they're together in solution, that weak electrolyte is actually going to ionize less than it normally would. So what we're going to do is we're going to look at an example. And in this example, it wants to know if the pH is going to increase, decrease, or stay the same when we add each of the following. So what we need to do first is we need to kind of think about what it means for the pH to increase or decrease. So when we have the pH increasing, that means that it's actually going to become more basic. When the pH decreases, that means it's going to become more acidic. Now let's also think about what this means in terms of H+. When it becomes more basic, do you have more or less H+? Okay, well, you actually would have less H+, because the H+ ions are what makes something more acidic. The more acidic it is, the more H+ ions that you have. This is going to be really important to think about so that you don't get tripped up on the wording. If you have to write everything out and label everything, please do so. So what we're going to do is we're going to start by looking at example A. So example A says that we have NaNO2. So we have sodium nitrite adding to a solution of nitrous acid. So what we need to do first is we need to figure out which is the strong electrolyte and which is the weak electrolyte. Well, NaNO2, this is a salt. Okay? A salt is a strong electrolyte. Anything with sodium is soluble. So sodium is always a spectator ion. Then we have HNO2. Again, this is nitrous acid. So this is a weak acid. So what we want to do is we want to write out the equilibrium, which I've already done for you down here. Write out the equilibrium reaction. So we have nitrous acid is at equilibrium with H+ and NO2 minus. Now, from this salt up here, what ion do we have in common? Well, we have NO2 minus in common. This is our common ion. So when we add the salt solution to this weak acid, we are adding more NO2 minus. We're adding more NO2 minus. So think about what happens with Le Chatelier's principle. When we add more NO2 minus, we now have too much of this product. Right? We have too much product. So what we have to do is we have to use this product up. So we're going to shift equilibrium to the left. We want to use up the products. If we're using up NO2 minus, we're also using up H+. So my H+ is decreasing. And my weak acid, we're increasing the amount of acid that we have. We're decreasing how much it ionizes. So if my H+ decreases, is this becoming more or less acidic? Okay, this is becoming less acidic, which means more basic. So what's going to happen to the pH? If it's becoming more basic, pH will increase. Okay, so what I want you guys to do is I want you to try B, C, D, and E. So pause the video, try those, and then come back and we'll go over the answers. Okay, so we can check answers with this example. So like we had already said in A, the pH is going to increase because we are using up our products because we're making more reactants. That's what Le Chatelier's principle says. So as we decrease the amount of H+, it becomes less acidic, so your pH is going to increase. Now with B, you're adding CH3NH3Cl. Well, notice that we have this CH3NH3 before the Cl, but we have a Cl. This is the salt. Okay? The salt is a strong electrolyte. It will break apart into its ions, and we have to figure out what the common ion is. So here is a base. Anything with NH2, if it ends with NH2, that's an amine, that's a weak base. So we have CH3NH2. when we add that to water, because we want to write out the equilibrium expression, CH3NH2, that's the base, that's going to accept a proton from water. It's going to become CH3NH3 plus OH minus. So looking at this salt, right, this salt is going to break apart into CH3NH3 plus and Cl minus. But anything with Cl is a salt and Cl is neutral. So we're going to be focusing on CH3NH3. We're going to be adding that. We're going to be adding that to the product side. So we're going to have too much on the product side. So equilibrium, again, is going to shift to the left. But now we're dealing with OH minus. So now we're using up OH minus. Okay, we're using up OH minus. So what that means, it's becoming less basic. As it becomes less basic, it's becoming more acidic. So as it becomes more acidic, your pH is going to go down. With C, you have sodium formate. So this is the salt because you have sodium at the beginning. So we're dealing essentially with formate adding to formic acid. So you're adding this common ion of formate. You have too much on the product side. It's going to shift to the left. It's not going to ionize as much. We're going to use up H+, very similar to example A. So because you're using up H+, it's becoming less acidic, more basic, so your pH is going to increase. Now with D, we have potassium bromide. We're adding potassium bromide to a solution of hydrobromic acid. Well, hydrobromic acid is HBr. What is HBr? It's a strong acid. It's not at equilibrium. So adding a common ion to an already strong acid is not going to affect the pH at all because it's not at equilibrium. So this is actually going to have no change in pH. And then E, you're adding HCl to a solution of NaC2H3O2. So HCl is being added. This is the strong electrolyte that you are adding to essentially a salt solution. Now again, remember, Na has no effect at all. So what we're focusing on is C2H3O2 minus. So we have C2H3O2 minus, that's a base, adding it to H2O. So C2H3O2 minus will accept a proton, and that gives us acetic acid and OH minus. So now we need to figure out what we're adding and where we're adding it. Well, if we're adding HCl, okay, HCl gives us H plus and Cl minus. Well, Cl minus doesn't matter. So what we're actually doing is we are going to add H plus to this acetic acid. We're adding H plus. So we're going to have actually too much of this acid. Again, this is like example B. Too much acid is going to cause a shift to the left. We're going to use up both of the products. So we're using up OH. It's going to become less basic, which means it's going to become more acidic. So what you want to make sure to do is, if you are not familiar with Le Chatelier's principle, maybe you just didn't learn it the first time, go back in your book, go back to the equilibrium chapter and review Le Chatelier's principle. Because everything with equilibrium and acid-base are still going to come up in this chapter. Okay, so what we're going to do is we're going to do an example together, looking at the common ion effect, and then I'm going to have you try some on your own. So this example says to calculate the fluoride ion concentration, okay, so that's going to be F minus, and the pH of a solution that is 0.20 molar HF and 0.10 molar HCl. So before we even worry about doing any calculations, what we need to do is we need to figure out what is the strong electrolyte and what is the weak electrolyte. So HF, what is HF? HF is a weak acid. You still need to know your weak or your strong acids and your strong bases. And then what about HCl? HCl is a strong acid, so what that means is HCl is going to completely dissociate into H plus and Cl minus. HF, because it's weak, is going to exist at equilibrium. So once we figure out the strong electrolyte and the weak electrolyte, we need to write the equilibrium equation for that weak electrolyte. So let's write it down here. So we have HF, which is aqueous, and that is going to ionize partially into H plus and F minus. Now remember, you might have plus H2O, and then this would be H3O plus instead. Right? It doesn't matter, just remember they're the same thing. So here's our equilibrium equation. Now what we want to do is we need to find the Ka. Okay, the Ka is going to be important once we start doing calculations, and because we have a weak acid, we need to know what that Ka is. So where can you find Ka values? Appendix D. So I'll just tell you the Ka for hydrofluoric acid is 6.8 times 10 to the negative fourth. Okay, now again, you would be given Kas on tests and quizzes, but you do need to know when you're doing work in class that you find it in Appendix D. Now, we have the Ka, we have the equilibrium. Now, what is the common ion that we're adding here? Well, here's the equilibrium. Here is our strong electrolyte dissociating. So what is going to be the common ion? Well, the common ion is H+. Right? They both have H+. So what we want to do now is we want to write the equilibrium expression for this equilibrium equation. So what we want to do is we want to write the Ka expression. Remember, this is Ka because you're dealing with weak acids. You need to make sure that you clearly label that. So Ka is going to be the concentration of H plus over F minus divided by concentration of HF. Right, that's equilibrium expressions that we've been working with. And we know now that numerically that is equal to 6.8 times 10 to the negative fourth. So this Ka will be useful once we get all of our equilibrium concentrations. So what we want to do next is we want to look at what our equilibrium concentrations would be. So what we need to do is we need to set up the ice table and we need to fill it in with the appropriate values. Now keep in mind that the initial concentrations are from the concentration of the acid that they're given and the initial concentration of the common ion. So what we have with this ice table is we have 0.2 molar of HF, but initially we also have 0.1 molar of H3O plus or H plus because HCl is also present and that ionizes completely into H plus and Cl minus. Now notice Cl minus doesn't matter because it's neutral. So then we're going to work through the ice table like we did before. So we have minus X for HF because it will somewhat ionize, and then we have plus X for the products. And at equilibrium, we have 0.2 minus X, 0.1 plus X, but notice what we did here is we assumed X is small. So we assumed that adding or subtracting X from 0.1 and 0.2 is not going to make a difference. Then what we can do is we can plug it in to the Ka expression. So 6.8 times 10 to the negative fourth was our Ka. And then we just used equilibrium concentrations for all of the concentrations of H plus, F minus, and HF. And when you rearrange and you solve for X, you find that it's 1.4 times 10 to the negative third. Now again, keep in mind what X is. Label X. Look back at your ice table and label X. So we know the numeric value for X, so let's label it. Okay, therefore, the concentration of F minus, which equals X, is 1.4 times 10 to the negative third molar, which means then H3O plus or H plus is 0.1 plus X. When you add 1.4 times 10 to the negative third, that really doesn't have much of an effect, so it's 0.10 molar. Now, for our purposes, we're going to assume that the hydrogen ion concentration initially is due entirely to the HCl because the HF does not ionize enough to have a significant impact on the H+. So the reason that we needed this H+ is because the problem also asked us to find pH. It asked us for two things. It asked us for the F- concentration, and it asked us for the pH. Now don't forget, these pH calculations, these pH equations are on the equation sheet. pH is equal to the negative log of H+. So we found everything it wanted us to find. Notice it's the exact same as what we did in the acid base, except instead of having 0 molarity for the initial concentrations of the ions, we just have one of them with an initial concentration. Okay, so what I want you to do now is I want you to try this example on your own. So it says calculate the pH of a solution containing 0.085 molar nitrous acid and 0.10 molar potassium nitrite. So pause the video and try this on your own. Okay, so what we're going to do is we're going to just go through the answer for this. So we know that we're finding the pH, which means that we probably will need to somehow find the H+ concentration. And we have 0.085 molar nitrous acid. So nitrous acid is HNO2. You still need to know formulas. You need to know polyatomics, you need to know your formulas, you need to know how to crisscross with charges. That all is still very important. And you have 0.10 molar potassium nitrite, so KNO2. Now, we need to label. HNO2 is a weak acid. KNO2 is a salt, which means it is a strong electrolyte, so it will dissociate completely into K plus and NO2 minus. Okay, and then HNO2 is our weak acid, so what that means is we need to write equilibrium expression for our weak electrolyte or our weak acid. So we have H plus NO2 minus. Now, if I look up in Appendix D, the Ka for nitrous acid is 4.5 times 10 to the negative fourth. So now I've written my equilibrium equation. I've found my Ka. Now I need to figure out what the common ion is. So I have nitrous acid and potassium nitrite. Okay, they both have NO2 minus. They both have nitrite. That's going to be my common ion. So I'm just now going to make my ice table. So initially I have 0.085 molar HNO2. I don't have any H+, but I have 0.10 molar nitrite. And that's because this is a 1-to-1 ratio. My salt to my nitrite is 1-to-1. So if I have 0.10 molar potassium nitrite, I have 0.10 molar nitrite ion. And then change is going to be minus X for the acid plus X for the ions. So 0.085 minus X, X, and 0.10 plus X. Let's make a note that we are assuming X is small. And now we can plug everything into our Ka expression. Okay, so we're going to use a new page because we started to run out of space. So 4.5 times 10 to the negative fourth is equal to products over reactants, right? So X for our H+. Because we're assuming X is small, we're just going to use 0.10 for the nitrite ion concentration. And then we're going to use 0.085 for the for the nitrous acid, because again we're assuming X is small. So we're going to rearrange. So when we rearrange and we solve for X, we get 3.825 times 10 to the negative fourth. Okay, so that's what I get for X. Now if we look back at significant figures, 0.085, this is 2 sig figs. 0.10, that's 2 sig figs. So my answer needs to be rounded to two significant figures. So I will have 3.8 times 10 to the negative fourth, and that equals x. But what does x equal? Well, x equals the H plus ion concentration. Okay, so here's my H plus concentration. Notice I labeled with units, but now that's not what the problem asked me for. The problem asked me for the pH. So the pH is going to be the negative log of that. So I'm going to use the entire thing, 3.825 times 10 to the negative fourth. And when we take the pH of that value, or when we take the negative log of that, we get 3.417. But because we want two significant figures, we want two numbers past the decimal, so we get 3.42. Okay, so there is the pH when we have the common ion. Now notice that our x was so small up here. Our x is so small that it's okay that we made this assumption that it wasn't going to have an effect because it is such a small number. If this number is -1 or -2 as the exponent, then we would actually have to go back and use the quadratic formula. But because it's less than 5%, we can make that assumption and it's okay. Alright, so what I want you to do again is I want you to actually do this entire example on your own. So you are calculating the formate ion concentration and the pH of a solution that is 0.050 molar formic acid, and I gave you the formula, and 0.10 molar HNO3. So I want you to go through step by step, label everything, write everything out, and solve for both the formate ion concentration and the pH. Okay, so you can take a look at my work for this third example when you're calculating both the formate ion concentration and the pH, which means you need the concentration of this ion, COOH minus, so you're solving for this X, and because you're solving for pH, you're going to also need to use the H plus concentration. So I set everything up. Formic acid is my weak acid. Nitric acid is going to be my strong acid. It's my strong electrolyte that's going to dissociate completely into ions. That's why you have a single arrow. I set up the Ka expression. Ka is equal to products over reactants. Ooh, I forgot to make one key note here. Assume X is small. All right, that's going to be important because I can assume X is small, so I can use 0.1 and 0.05. When I solve for X, again, label it, make sure you know what that represents. X is equal to 9.0 times 10 to the negative fifth. I use two significant figures because both concentrations, 0.050 and 0.10, these are both two significant figures. So 9.0 times 10 to the negative fifth molar is equal to the formate ion concentration. Then we use that for H plus. So 0.1 plus 9 times 10 to the negative fifth, that's so small it doesn't matter. So it's essentially equal to 0.1. Now I want you to take a look at what I did here. I changed it to scientific notation. 1 times 10 to the negative first. Negative log of 1 times 10 to the negative first is equal to 1. That's actually equal to the exponent. Remember, pH and pOH can't be negative. So pH is equal to the negative log of 1 times 10 to the negative first. That's equal to 1. So you have your concentration and your pH, and that answers this question. Okay, so I want you to actually do example 2 in the notes on your own. So using the equilibrium constants from Appendix D, I want you to calculate the pH of the solution that contains 0.060 molar potassium lactate and 0.085 molar of lactic acid. So go through and label everything. Actually, I've already given you your equilibrium expression. Figure out what the common ion is and solve for the pH. I want you to bring this example finished to class with you, and then we can go over any questions that you might have. Now, just to ensure that you understand the common ion effect, there are 5 problems in your book that you can look at. So 1, 14, 16, 17, and 18. And again, the common ion effect, if you haven't been able to tell, is simply using acid-base equilibrium that we have utilized thus far in class, except now you're just starting with an additional initial concentration. But I want you to use this time, the rest of today, to look back over anything that you still might need practice on. So maybe it's Le Chatelier's principle. Maybe it's using these ice tables to find pH. But look back in your notes. We're actually going to be going over the tests in class. But I want you to use this time. I want you to think about what you need to practice to ensure that you will do well with this chapter.